Okay, so welcome to all of you and good evening. This is the week 9 of the course Earthquake Geology, a tool for seismic hazard assessment problem solving session. So, in today's session, or problem solving session, we'll discuss about like mainly about the shear faults, because this is the topic that we haven't discussed so far. So all the previous concepts that we have learned so far would be helpful to understand this complex strike slip system and how the shear zones are formed and what are the landform features that we got from this complex strike slip fault system. So all those things will be we will understand in this session. So first we'll start with question 1, that is and this question is related to that how the fault is relating, or for like how fault can be a cause for a river to change its path. Okay, so this first question states that the lateral propagation of fault along the strike is responsible for the disruption or deflection of the major river, leaving behind the signature of. Okay, so what are the major keywords of this question is that that how the fault is disrupting okay, so how the fault is creating disruption and deflection of major rivers, or just leave it to the river path. So the options that we have is the point bar, avulsion, wind gap, and all of the above. So I believe that this point bar you have already heard about it and you have already learned about it, but let's have a quick recap of each and every terminology, and then we'll come to the correct answer of this question. So what is the point bar? So can anybody tell me like what is the point bar? Yeah. Yeah, at a particular point. So it's majorly if we have to define it, so it's a depositional kind of feature, okay, that deposit along the river path. So in this, from this illustration we can see that this is the river channel which I am marking with blue marker. So this is a meandering river because its path is not straightforward, it's a sinusoidal kind of path it has. So what happens that whenever there is a meandering, so the area that is inside the river stream where the sediments will get deposited, and the area that is outside the stream, for example over here you can see, so this particular area is outside the stream, and specifically the area which is present when the river path is getting changed. So here you can see like from this direction it is converging to this direction, so this is the point where the path is getting changed. So this point maximum erosion will happen, and that's why we see the features like cut bank at this particular area. But the area, in a similar way, the area which comes inside the stream, when the stream path gets changed, here we find point bar where the sedimentation happens. So it is a depositional features. Okay, always remember that point bar are the depositional features made of alluvial or whatever sediments river carry. So it mainly carry the alluvium sand deposits, and that accumulates on the inside band of the stream and rivers. And as we have already seen that they are majorly formed in the case of the meandered river, because for the case of the straight river path there would be no point where the point bar can form. So the main feature that is required for point bars to be formed is that stream should be meandering. Okay, and one key feature of about this point bar is that the depositional sediments are well sorted. So remember that the sediments that deposited in the point bar are well sorted. And if we would like to conclude that point bar is an area of deposition and cut bank is the area of erosion, which is quite evident from this figure, that here the erosion is happening, the area which is outside the stream, and the area which is inside the stream, depositional is happening. Okay, so we have understood what are the point bar. So from this overall discussion we can see that no change in path or the deflection of the stream is happening. So definitely point bar is the not correct answer for the above question. Now let's move to the Okay, hi Jasurya. Yeah, good evening. So we have started the session. So I think we were just discussing the first question. So I think we can just see the questions just to give you a brief about what we were discussing. So the question was the lateral propagation of fault along the strike is responsible for the disruption and deflection of the major river, leaving behind the signature of dash. So here we are trying to identify the answer or the landform that is happening due to the lateral propagation of the fault and its impact on the river path or the stream path. So we were discussing the first option, that is the point bar, and I hope you have already know about the point bar. So now moving forward, let's understand the avulsion or the second option of the question. So avulsion is a interesting process, and remember that it's a natural process. So here no secondary effect is happening. So what happens in avulsion, like river stream change its path, and why it changes path, that we will see. So it's a natural process by which flow diverts out of an established river channel into a new permanent course. So if we'll see this figure, so let's understand the first subset of the figure, that is the A part. So this is the parent channel or the main path of the river. But now imagine a scenario where due to some obstruction, so if some obstruction comes, for example in this B section, here you can see that there is a obstruction is present at the mouth bar of the deposition, and due to which stagnation happens. So now what would be the tendency of the river? Its tendency is to find the least resistive path. So it tries to avoid this path and look forward the new path. So this would be its finding phases, like it can go up to this direction, this direction, this direction. Now if we come to the C section, so after this finding phase, it identifies the most or the least resistive path, which will act as a daughter channel or the new permanent course of the river. And with a course of period or with course of time, this earlier channel will get completely abandoned and this new channel will act as the primary river channel. So this whole process is called as a avulsion. So here what happens, the new course is adjacent on the floodplain, abandoning the former channel. Okay, and this process is not a very fast or the quick process. It happens like for a decadal scale or to millennia scale, and the main mechanism that favors this widespread distribution and the storage of fluvial sediments. So imagine that if this channel was the primary channel, so definitely sediments were there. So here you can find a lots of sediments. Even this channel is now abundant, but sedimentation will be there. So through this process, it spread out its flood channel, and also it enhanced its capacity to store a larger amount of sedimentation, because now the sediments can deposit over here, and now since this one is the active channel, so now the sediments will start deposited over here, and in future it might be happen that this channel will also get abundant and it again identify the new channel. So now you can find the sedimentation in 3 channel. First one here, then second one here, and the third one, suppose this would be the new active channel, so here. So this is how the sedimentation increases with the help of the avulsion. Now moving to the third option that we had is the wind gap. So what is the wind gap? Anyone has any idea about this? Or from this, seeing this images, can anybody guess what is happening? Okay, so if we'll read the definition first. So wind gap or air gap is a gap. From this even term is also quite clear that it's a gap through which water wave once flowed and now it's dry as a result of stream capture. Now what is this stream capture word? First let's take a image that I have taken from the Wikipedia. So in this first figure, or the top one figure, you can see that a river is flowing like this. So this is the main channel, but due to some event or some tectonic process, and there the fault could also play an important role, this path got changed, and now what path is following? This is following this path. So that change in path is called the wind gap. Now one must ask that even in the earlier process, for example in avulsion also, this same kind of phenomena was happening, but this avulsion is a natural process, okay, but this wind gap is the process that happens when certain certain tectonic process happens, or the repercussion of the tectonic process. From the repercussion of the tectonic process I meant, for example, now let's come to the second figure. So this would be A, this would be B, and this would be C. So in A, this is the original or the earlier way the river was flowing, okay. Now what happens, like due to some upliftment, and this upliftment might be happen due to the thrust faulting. So due to that thrust faulting, this rich kind of phenomena has created or has formed in the path of the river. Now what options river has? River has the option to cut through it, this landform, and try to continue its path, but since the pressure of the river stream is not very high, so it takes lots of time to cut through that solid rock mass and then pass through it. But once it cut it, so here you can see that there is a it's just a like imagination. So you can imagine this, now in this wide space what would be there? Wind or air would be there. So that's why we called a wind gap or the air gap, because earlier there was a rock mass, but since it was coming in the way of the river, so river has cut that rock mass, and now there is a void present in that particular rock mass. So that we called as a wind gap. So this wind gap might be happen due to the faulting, or when when some tectonic activity happens, so due to which the path of the rivers get changed. So if we will try to answer the question, that the lateral deposition, and this can be understood from the simple like strike slip faulting figure. So suppose this is the fault plane. Now since we are talking about the strike slip, so it will displace along the horizontal direction. So imagine that river is following like this and it's continuing its path, but due to the movement in this strike slip faulting, so this block moves here and this block moves over here. So now what would be the after effect scenario? So since the river is moving like this, but now its path changed like this. So this process is called as a wind gap, because here now gap has been there with respect to its initial path. So the answer for this question is the wind gap, and that is happening due to the strike slip faulting, because it produce the horizontal displacement, and also it can be happen due to the reverse faulting as well. And the same thing we have discussed in this figure, like due to the thrusting, some upliftment might happen, and this upliftment also could lead to the creation of wind gap. Now moving to the second question, and I would request you to play to pay a bit more attention, because this is the concept very new to us, so we will understand very slowly. So what is so anybody of you know what is the radial shear fractures? Anyone? No, okay. So we will understand today. Okay. So the question says that radial shear fracture will form having angled around 15 to 20 degree with respect to the main line of faulting, or principal displacement zone is called. So to answer this question, first we need to understand what are the radial shear fractures. And the option that we have for this question is the antithetic strike slip fault, synthetic strike slip fault, dextral fault, and sinistrial fault. So we will understand each and every term all as well. So first let's go to the very basic and understand the simple thing, that is the dextral and sinistrial fault. So this is the very basic like subsection of the strike slip fault, or the categories of strike slip fault. So I hope you know that how we can designate a fault as a dextral strike slip fault or the sinistrial strike slip fault. So if you want me just to give you a brief, so if you are standing on this side of block and looking the adjacent block or your just opposite block, and if it is moving towards your right hand side, then it's a dextral strike slip fault, and if it is moving your left hand side, then it is a sinistrial strike slip fault. Okay. Now let's understand these two further categories of the strike slip fault, that is the antithetic and synthetic. Okay. So just ignore the heading, I forgot to change it. So okay. Now this is a bit complex figure, but it's a very easy one. So here first understand that we have two blocks, and what are the two blocks? These green blocks that you can see. Okay, so these are the two blocks. So we can see that the upper block is going towards the right hand direction, and this lower block is going towards the left hand direction. And if we, since it's a strike slip fault, so we can mark it whether it is a dextral or the sinistrial. So if I'll comment on its movement, so it would be the dextral strike slip fault, right? Is clear to all of you that it's a, forget about this yellow figure, just focus on this green blocks that we have. So whether it's a dextral or the sinistrial, can anybody say? Yeah, it's a dextral. Okay. Now, so this is the major fault plane that we have. So what we also called, apart from the fault plane, it's the principal displacement zone. Okay, and in short form we write it as a PDZ. So this direction would be my principal displacement zone. So far so clear? Okay. Now if I'll try to create, so I'll mark that principal displacement direction as Y, that is written over here in this figure. Now what happens, that whenever there is a shear stress is applied, these conjugate shear fractures form. And what are these conjugate shear fractures? These are the radial shear fractures. And how we can mark it? With the abbreviation R. So here we have the principal displacement direction. So this would be my so this is my Y. So this conjugate fault would be my R, that is the radial shear fracture. And the sense of movement of this radial shear fracture would be same as the main displacement fault direction. So if main displacement fault direction is like this, so this radial shear stress direction would also be like this. Okay, and that's why it called as a synthetic, means the same. Syn here, syn means the same direction. Okay, now the conjugate part of this radial shear stress or the fracture is the P shear. So if I have to draw a conjugate of it, so definitely it would come like this, and that fracture would be marked as P. So now so far what we have a Y, that is a principal displacement zone or the direction, and this R is the radial shear fracture, which is the first subsidiary fracture to this main displacement. And why this fractures is happening? Because there is the shear stress is accumulating, and once there is a shear stress is getting accumulated, then it's obvious that fractures will create to accommodate that extra stress. So the first fracture that will create would be the radial shear fracture, and the direction of this radial shear fracture would be same as the main fault direction, and that's why it is called we are calling it as a synthetic. And the conjugate of this radial shear would be the P shear. Now if we'll talk in terms of angles, okay, so the angle between this Y, and now we will measure the angle with respect to the main displacement zone. So the angle between Y and this R would be around, in general it around 10 to 20 degree. Okay, and here it's 10, not 1, I have wrote it 1. So it's 10 to 20 degree. And if you see the sense of direction, so it is in the clockwise direction, right? Because clock moves like this, so this is in the clockwise direction. If this fault is the dextral fault, but if this fault is a lateral fault or the sinistrial fault, then this whole direction conventional gets changed. Now how it gets changed? So imagine, now I am out of space. Okay, let me draw here. So suppose now it's a lateral fault or the sinistrial fault. So if it would be a sinistrial fault, then the direction would be like this, and this would be like this. So, and if I have to draw, then what will happen? Now the R would be here and this P would be here like this. So you can see that it's got completely opposite, or it created the mirror image. So what we are here considering, that it's a dextral strike slip fault, and if this R will happen or the secondary fracture will happen, then its direction would be in the anti-clockwise. And for P, its sense of direction would be here it should be, for R it should be clockwise, and for the P it should be anti-clockwise. I think things are clear so far. Now if you have any question, then ask. Then I'll move forward after that. You didn't get that? Why? P is anti-clockwise direction. Okay. Yeah, we are measuring from the Y. y is a like focal point. Okay, yeah, to assess the every sense of movement. So you can see that like with respect to y, it's in the anti-clockwise direction, like p. Here, that's why I was saying na, like in terms of sinistral, this is case for the sinistral. If we talk about the sinistral, then every direction will get just opposite. So for dextral, if our direction is in the clockwise, so for the sinistral it would be anti-clockwise. Just remember in that way. Okay. Yes. Jasurya, are you there? Are you understanding? Okay. So that's why this R and P are the synthetic secondary shear fractures. Okay. And if we about the R dash and P dash, they are the antithetic faults because their sense of movement is just opposite to the main sense of movement. And here the main sense of movement like this, that is the sense of movement for the principal displacement zone. So these are the two major categories under this strike slip fault, that is the synthetic and the antithetic. And if we talk about the timing of their formation, so first the synthetic fractures will create, and even in synthetic also first the radial shear fractures will create or will form, that is the R. After that P will get formed and then R dash and P dash. So that would be the sequence of their formation. And if we talk about the R dash angle or its orientation, so for the R we have seen that it forms at the angle around 10 to 20 degree, but if we talk about for R dash, it forms around at the angle 75 degree. That you can also see from this figure, like if we will try to measure the direction, and here we will try to measure the direction like this way, because from this way it would be the closest to the main displacement zone. So if we will try to see the direction, then it would be around because here it is around 10 to 20 degree, then we have to subtract it from the 90 degree, so it will come around 75 degree. So its orientation is at the high angle, that is around 75 degree. I think the concept is clear. So okay, now you guys will answer the question. Now tell me, what would be the answer of this question? We have understood what are the radial shear fractures. Now they are asking that they are forming around 15 to 20 degree. So what would be their what they would be called as? Definitely dextral and sinistral is not the correct option. So would it be synthetic strike slip fault or the antithetic strike slip fault? First tell me what is the meaning of synthetic and antithetic. Correct. So now what would be the answer? Answer would be B. Correct. So Jasura, have you understood, have you learned this concept before? Okay, yeah. Okay, good. Akshay, have you understood that why it is synthetic? It's simple. It's just opposite to synthetic. Like when the direction of the fault or the secondary fracture that has been created, that is R dash, and its sense of movement is just opposite to the principal movement direction or the bulk movement direction. So like if you see this fault, so arrow like this, and if I'll try to mark that it's a sinistrial fault system, correct? But our major fault system has the direction of dextral direction. So that's why they are antithetic, because anti means opposite, yeah, anti to the bulk direction or the major principal deformation direction. Now this is our last question. The question says that in a dextral strike slip environment, dash and dash will form in a releasing band. So first, for what we have to see that what is the overall picture look like in the case of the dextral strike slip environment, because so far we have only understood what is the dextral strike slip fault, but here we will see whole dextral strike slip environment. Now what kind of landform or the features form in this environment? So the options are pull apart basin and normal fault, pressure ridges, thrust fault, pressure ridges, normal fault, and pull apart basin, thrust fault. I hope this fault terminology is clear to everyone, but this pull apart basin and the pressure ridges, since we haven't discussed in this session so far, so we will first understand this. So this is the overall strike slip fault system. Now why it is a fault system? Why I am saying fault system? Because here you can see we have a 3 faults. Where are these three faults? First one is here, second one is here, and this third one is here. Okay, so tell me what like this first fault system, what kind of fault it is, like strike slip, sorry, dextral or the sinistrial? Answer quickly. Now I think you can answer it quickly. Dextral. Similarly for the second one and the third one, because if you are standing over here, so this block is moving in the right hand direction. It's clear that how we can see the sense, because now we can't see the block, so it would be might bit what I say, okay, it would be bit difficult, but I think you can imagine, correct? So all these 3 faults are the dextral strike slip fault. Now let's understand, now we'll analyze the whole picture in a single frame. So if we'll see first this portion, okay, so here what is happening, this lower block of the first fault system is moving in the left hand direction, correct, and the upper block of this second fault system is moving in the right hand direction. I hope you are getting that what I meant by the upper block and the lower block. Clear to everyone? Okay. So here what kind of system is creating? It's a extensional environment, because the direction are pushing away, they are stretching away. Okay. So this is the extensional environment. In a similar way, if we see the second scenario over here, where they could connect, or here the connection will form, and how we will form we will see later on. So, we will see the direction of the upper block of the second fault is in the right hand direction, and we will see the direction of the lower block of the third fault system, it is going towards left. So, what kind of scenario is happening over here, or this stress scenario? It's compressional. Okay. So far we have seen that in the extensional environment, in general or most of the time, normal faults, we see the normal faults. And in the compressional environment, what kind of fault we generally see? The thrust fault, thrust or reverse fault. Okay. ठीक है, we have understood this kind of phenomenon. Now, earlier the connection was, or there was a soft linkage between these two faults. These two fault means first and the second fault. And what I meant by the soft linkage, that there is no actual physical fault is present over here. Now, due to the shear zone, there is a connection that we called as a soft linkage. Soft linkage. So, on the both side we can see the connection is the soft linkage, but over the period of time when the stress gets increased, we can see that fracture can form or the fault can form, which provides the hard linkage, or now there is a physical connection between this fault 1 and the fault 2. So, now we can see that their fault has created on both sides of the fault system that we had. Now, once this fault has created, now comes to the third stage, that is over here. So, this is my third stage. So, in the first stage we have a soft linkage between these strike slip fault and specifically dextral strike slip fault. In the second scenario, the hard linkage was formed between these strike slip fault system. Now, in the third scenario, now landforms are created. And what are these landforms? That since you can see that in this part or in this portion, we have already identified that extensional environment is there. So, in the extensional environment, when there is a pulling force are acting, the kind of formation that we see is the pull apart basin. And what are this pull apart basin? It's looks like this, or the normal basin system, where the sedimentation can happen in this depression zone. So, these are the pull apart basin, and along this pull apart basin there would be the normal fault. And why there would be normal fault? We have seen that in the extensional environment normal fault gets created. On the other hand, if we will see the compressional kind of scenario, or which is acting over here. So, here rather than pull apart, what will happen? The push up, because there is a compression. So, due to compression, the ridge kind of phenomena will create, or something upliftment you can see on the compressional side. And along with this upliftment or the ridge kind of features, you will also see the thrust faults. Okay. Now, there is one keyword present on this whole. I think we have understood most of the terminology, but this right steeping and left steeping we haven't understood. So, let us understand what are these. Though they are not related to the question, but I thought of, since we are discussing this strike slip fault system, it would be good we can understand the whole concept. Again, please avoid this heading. Okay. So, this is the concept related to the right steeping. If we see, just focus, avoid this aneglon fault system. If we will see simple right steeping, what does it mean? Now there the steps are forming, okay, the normal staircase you can imagine. So if you are standing on this staircase, the top one, and looking to this below one step case, would it be appearing your right hand side or the left hand side? Imagine and tell me which side it is appearing. Yeah, right hand side. Be confident. Yeah, it's the right hand side. It's a normal thing. So it is coming at your right hand side. So that's why it is right stepping. And how it is related to the earlier figure, we will come to that. Now, in a similar fashion, now imagine you are standing on this staircase. Okay. So on which side this staircase would come? On your left or the right? Definitely on your left hand side, correct? Now if we will again go back to the above figure, now we have first staircase here, and to come at the second fault system, we have to take a staircase like this, correct? So that would be your right stepping, and from this fault, now we would move to the third fault. So for that, this staircase would be like this, correct? So this would be the left stepping, the same concept that we have seen over here. Clear to all of you? Okay. Now this is the aneglon fault system that we have discussed. Now in the case of the left lateral or the right lateral, the sense of direction would be different. How? Suppose this is the main principal deformation zone, and your fault direction is like this, means it's a sinistral fault, or the other name is left lateral fault, and it's equivalent to your sinistral fault. I think I wrote this spelling incorrectly, just correct it. Okay. Now your fractures are forming like this. Now if you try to make them flat, so how you can make them flat? By moving like this, correct? Though it's not related to the concept that we have been discussing, it's a different thing. So if you have a fracture like this, so, and if you want to make them flat, definitely you have to push them like this, correct? So to push them like this, so they are you have to move them towards the right hand direction. So that's why it is right stepping. Similar way, here for the right lateral fault system, your fractures or the radial shear fractures that we have discussed earlier will form like this. Okay. Now if you have to move them, make them flat, you have to push them like this, in this way, or in the left hand direction. So this is how you can comment on their steeping direction, whether it would be the right steeping or the left steeping. So there is a one kind of system that is formed for the aneglon fault system, and this is the other kind of fault system that is present in the lateral fault system. So this is how you can comment on their direction, whether it would be the right steeping or the left steeping. So okay, moving further, if we'll continue the same discussion. So this is again strike slip tectonics, and we have already seen that on the left hand side direction, what we were seeing, the basin kind of feature, and that you can see that there is a depression like this. This has a depth as compared to the right hand direction, where due to the compression this ridge kind of an landform has been created. Okay. Now if we'll see that pull apart basin may eventually lead to the plate separation along the system of side steeping spreading center. So since now there is a extensional energy is working, so in future it might be happen that these two blocks can get completely separated, and once they establish, they subside very quickly and accumulate large thickness of alluvial and or lake deposits. And if we talk about the ridge system, so these are the local shortening that will produce vertical lengthening and thus surface upliftment, and this push up area will be eroded. So like due to erosion in future it might be a possibility that it got completely eroded, but in this scenario there might be a possibility that it can get completely apart or separated. Now you can see that complete boundary over here and no basin would be present in that scenario. But this push apart basin are very important place if we will talk about the mineral deposition, and in mineral specifically the oil and gas deposition, where we look for the a good amount of basin where the highest sedimentation can happen, because this sedimentation will act as the conversion of the organic matter into the petroleum resources. So this is the whole strike slip tectonics that you should remember, that what kind of features we see in this strike slip tectonics. So if we go back and try to answer this question, so we have already seen the dextral strike slip environment. So what would be the correct combination? Now tell me. Pull apart basin and normal fault. Correct, because pull apart basin and normal fault both will happen in the case of extensional energy, and this pressure ridge and thrust fault will also be, but in the case of contractional or the compressional. But this combination that we can see in the third option, that pressure ridge and normal fault cannot be happen, because along with pressure ridge definitely you will see the thrust fault, because this is the compressional environment. So this combination can never happen. Similarly for the fourth option, that pull apart basin and thrust fault together cannot be happen. So I hope you have understood this whole strike slip system that we discussed. So anybody has any question?